In this lesson, we will use some algebra techniques to evaluate limits. We saw in a previous lesson that if you have a limit of a rational function, oftentimes you can evaluate the limit by using direct substitution. That is, by plugging in the limiting value of x into the function to get the value. But this only works if you're not dividing by 0 when you substitute in the limiting value of x. So now we will look at some examples of how algebra can be used to help us evaluate limits of this type. Consider the following limit. We're going to look at the limit of x squared plus x minus 2 all over x squared minus x as x approaches 1. This is a rational function, so we might try to do direct substitution. But if you notice, when you evaluate this expression at x equals 1, in the numerator you'll get 0, which is not a problem. The problem comes when you plug in 1 in the denominator and you also get 0. So 0 over 0 is not an expression that you can evaluate. So we can use some algebra techniques to evaluate this limit. We notice that since when we plug in 1 for x, that both the numerator and denominator equal 0. So we see that there must be a common factor of x minus 1 in the numerator and denominator. So if we factor the numerator and denominator and cancel the common factor x minus 1, we'll get a limit with an easier fraction that we actually can evaluate by direct substitution. So let's proceed. So we're going to factor the numerator and denominator. So the numerator factors as x minus 1 times x plus 2. And the denominator, there's a common factor of x, so it factors as x times x minus 1. Now we're taking the limit as x approaches 1. So recall, when we look at limits, we're not concerned with the value 1 for x. We're only interested in what happens as x approaches 1 from both sides. So as x approaches 1 from either side, either from the left or from the right, in the limit we won't be dividing by 0, so we can actually cancel the common factors of x minus 1. And so this limit that we started with actually can be reduced to the following limit. The limit as x approaches 1 of x plus 2 over x. Now this limit has a rational function, and we will not be dividing by 0 if we plug in x equals 1. So we can evaluate this using direct substitution. By direct substitution, I can plug in 1 for x, and when I simplify this, I get the limit is 3. Let's look at another example of how we can use algebra to simplify the limit of a rational expression. Consider the limit of the quantity 4 plus h squared minus 16 over h as h approaches 0. This type of limit might look familiar when we first talked about finding the slope of a tangent line or the slope of a curve at a point. So these are the type of calculations that will be needed to find slopes of tangent lines, in other words, to find derivatives of a function. So if we try direct substitution with this rational expression, the numerator will equal 16 minus 16, which is 0, and divided by 0. So we can't break this up as the limit of the numerator divided by the limit of the denominator. But we can use algebra to simplify this limit. Let's multiply out the numerator. It's best to think of this as 4 plus h times 4 plus h, and then use the FOIL method to multiply these two polynomials together. A common mistake is to square both terms, but 4 plus h times 4 plus h will give us 16 plus a total of 8h plus h squared, and then I'm still subtracting 16 in the numerator, and the denominator remains h. So we can simplify the numerator. There's a positive 16 and a negative 16 that I can cancel. And we notice that the two remaining terms in the numerator, 8h and plus h squared, have a common factor of h. So I can factor out a common factor of h, and the numerator and denominator have a common factor of h that I can cancel. And I'm left with the limit as h approaches 0 of 8 plus h. But this is a polynomial, and so I can evaluate this using direct substitution. So all I need to do is plug in 0 for h, and by direct substitution, I get 8 plus 0, which reduces to 8. So the limit of 4 plus h to the quantity squared minus 16 divided by h as h approaches 0 equals 8. This next limit is similar to the previous one. It's actually a computation you will see in the future when we evaluate the derivative or the slope of a tangent line at a point on a function. So this expression is another rational expression, and if you want to try to evaluate it using direct substitution, you'll see that if you plug in 0 for h, you'll end up with a fraction that looks like 0 over 0. So we need to apply a little bit of algebra techniques before we can evaluate this limit. So when dealing with limits of this type, where there's a radical and there's more than one term in the numerator or denominator, the trick is to multiply the numerator and denominator by the conjugate of the radical expression. So this expression, the radical expression I'm talking about here, is the square root of 1 plus h minus 1. The conjugate of this expression will be the square root of 1 plus h plus 1. So all you have to do is change the sign between the two terms. So I'm going to first multiply this fraction by the square root of 1 plus h plus 1 divided by the square root of 1 plus h plus 1. So you must make sure that you multiply both the numerator and denominator by the same expression, because I'm really just multiplying by a factor of 1, and so the limit should stay the same. But this will create a rational expression that we can actually evaluate using direct substitution. So now let's simplify this expression. So I get the limit as h approaches 0. Now the numerator I'm going to multiply together using the FOIL method. I'm going to multiply square root of 1 plus h times square root of 1 plus h, and that'll give me, the square roots will cancel out, and I'll just get 1 plus h. Then I need to multiply the square root of 1 plus h times 1, so I'll get plus square root of 1 plus h. Now I need to multiply negative 1 times square root of 1 plus h. This will give me a negative square root of 1 plus h. And finally, I need to multiply negative 1 times positive 1, and this will give me minus 1. In the denominator, I don't want to multiply out h times the denominator square root of 1 plus h plus 1. I'm just going to simply write them together as h times the quantity square root of 1 plus h plus 1. Now let's simplify this rational expression. So a lot of stuff cancels in the numerator. We have a plus 1 and a minus 1 that will cancel. We have a square root of 1 plus h and a minus square root of 1 plus h. The only term that's left is the term h. So this expression simplifies to the following limit. H divided by h times the quantity square root of 1 plus h plus 1. So the numerator and denominator has a common factor of h, which I can cancel. So when I cancel the h in the numerator, I need to leave a factor of 1. So this simplifies to the limit as h approaches 0 of 1 divided by the square root of 1 plus h plus 1. So this is equivalent to the original limit. But now, if I try to solve this limit by direct substitution, I'm no longer dividing by 0. So I can evaluate this expression using direct substitution. So by direct substitution, I can plug in 0 for h, and I get 1 divided by the square root of 1 plus 0 plus 1. Well, the square root of 1 plus 0 is just 1, the square root of 1, which is 1. So this expression simplifies to 1/2. So this example illustrates how you can use algebra to solve a limit of a rational expression involving radicals. I'm going to show you another way that you can evaluate this limit without using algebra. It relies on your knowledge of what a limit is and the use of a calculator. So again, suppose we want to evaluate the limit as h approaches 0 of square root of 1 plus h minus 1 all over h. So we saw that the trick to evaluate this limit is to multiply the numerator and denominator by the conjugate. So let's think about what this expression means. We're taking values of h very close to 0, and we want to see what does this expression, square root of 1 plus h minus 1 all divided by h, what value does that expression get closer to as we take values of h very close to 0? So we saw that the answer was 1/2. Let's see how we could do this using a calculator. So what we need to do is plug in values of h. I'm going to make a little table here. Let's take values of h, and we're going to take values very close to 0. And we're going to plug them into the expression, let's call it f of h. So f of h is going to stand for this expression in this limit. So let's take values very close to 0. Let's take some positive values like 0.1, 0.01, and maybe one more smaller value like 0.001. And let's do the same thing on the other side of 0. Let's take values like negative 0.1, negative 0.01, and negative 0.001. So I'm going to take these 6 values of h, and I'm going to plug them in the expression square root of 1 plus h minus 1 all divided by h. So now let's look at the table of values of f of h for these values of h that I plugged in. We see when h is 0.1, f of h is 0.488. When h is 0.01, we get 0.498756, and 0.001 f of h would be 0.499875. So as h gets smaller positive, we see that the values of f of h are getting closer and closer to 0.5, which is 1/2. Let's look at the negative values that I've chosen for h. If I plug in negative 0.1, f of h is 0.513. If I plug in negative 0.01, we get 0.5013. And then as we get closer to 0 from the left, negative 0.001, we get 0.5001 for f of h. So we see that using a calculator, this confirms our calculations that we made by using algebra alone. So using this technique, you can evaluate a lot of limits, but we also need to be able to justify our limits by using algebra. So we see that this limit should equal 0.5 or 1/2.